All right, good morning, everyone. My name is Vivian C. I'm a faculty member in the EECS department here at MIT. And today I'm going to tell you a bit about our work on efficient computing for AI and robotics. This work is in collaboration with Surtesh Karaman, who's a faculty member here in the Aero-Astro department, Joel Emmer, who's also a PI here in CSAIL, and Thomas Helt, who's a faculty member in the Institute of Medical Engineering and Science at MIT. So there's been a lot of exciting applications for AI and robotics over the past few years, and a lot of the processing for these particular applications tend to happen in the cloud. But there are many compelling reasons why we would want to move the processing from the cloud in the data center to the edge and into the device itself. So the first thing is that if we want these technologies to be accessible to the people around the world, we want to reduce the dependence on a strong communication infrastructure because that's not actually feasible. So if we can bring the compute locally to the person, that becomes more accessible. Another reason is that for a lot of these exciting applications in AI, particularly in the healthcare space, we're often dealing with very sensitive information that we're collecting, and we might not want to necessarily share it to the cloud. So in order to preserve privacy, we want to move the compute to where the data is actually at. So again, another reason why we want to process near the edge. Finally, for a lot of exciting applications, particularly in the robotics space, it involves interaction with the real world. And as a result, we're very sensitive to reaction times. And so you can imagine for an application such as self-driving car, as you're going down quickly down the highway, if you encounter an obstacle, you might not have the time to send the data to the cloud, wait for it to be processed, and to come back and to stop the vehicle. So low latency is really key when you're trying to interact with the real world. And that's another reason why we want to move the processing into the actual robot or vehicle itself. But one of the main challenges of moving compute into the robot or the device is actually the power consumption. So if we take the self-driving car as an example again, we can see that in a self-driving car, it actually consumes more than 2,000 watts of power just for computing. So this is just to crunch through all the data that's collecting through its sensors, and this generates a lot of wasted heat. And even in some cases, we need to use water cooling to reduce this heat that's generated by the compute. And you can see that it takes up, the whole trunk of an actual vehicle. This challenge becomes even more severe when we think about devices that are much smaller in scale. So for example, a device that can fit in the palm of your hand. So for example, a smaller robot or even something like a smartphone. In these particular devices, we're limited in terms of the amount of energy that we have because the battery size is limited by the size and weight of the device. And then if we look at existing processors for these types of applications, often they consume an order of magnitude higher power than what's typically allowed for these handheld devices. So for thermal reasons, typically these devices are limited to under a watt of power consumption for compute. So in the past, the way that we addressed this was actually we allowed for Moore's law and Dennard scaling to give us faster, smaller, and more efficient transistors. And this has allowed us to sustain a growth in efficiency and speed over the past few decades. However, this past recent decade, we've noticed a significant slowdown in Moore's law and Dennard scaling. So as a result, the faster or more efficient transistors are not going to be able to carry us forward to meet the growing demand of compute for AI and robotics. So we need another solution. So one of the focuses within my own research group is to look at how we can deliver energy efficient AI as well as efficient robotics through a cross-layer design approach, which means optimizing across the entire stack. That first involves looking at designing new algorithms that also account for energy cost and computing cost in addition to achieving high accuracy. It also means that we need to redesign the computers from the ground up and develop specialized compute hardware specifically targeted at the tasks that we care about. So this could also be referred to as domain-specific hardware. So these pieces of hardware really involve focusing on tasks like AI and robotics, and this involves new computer architectures as well as new circuits. And then finally, it's also really important to think of the integration of this new compute hardware into the system itself. So and look at the interplay between sensor power and compute power. And if you're thinking about robotics, also the actuation power as well to get an overall holistic, energy efficient system. So if we're going to redesign the computers from the ground up, the question we should be really asking is actually where is the power consumption going? So as it turns out, the power consumption is actually dominated by what we call data movement. So often in a lot of these types of applications, you're doing a lot of operations like multiplications and adds, and you can reduce the energy for performing a multiplication add by reducing the precision. So shown here in blue is the energy consumed for these various operations. However, what you'll notice is that it actually costs more energy to read data from the memory and deliver it to these compute engines than to perform the computation itself. So for example, reading from a 32-bit SRAM, which is only 8K bytes in size, a pretty small SRAM, would cost 5 picojoules in energy, which is already more than the amount of energy that you would actually expend doing the multiplication and addition. And of course, if you're trying to move the data from off-chip memory, let's say DRAM, which you typically need to use for higher density memory, you're talking about orders of magnitude higher energy cost. So the real takeaway here is that it's not just the computation, not the multiplies and add operations that are consuming the power, but actually data delivery and moving the data around is much more expensive. And that's what we really need to address if we're going to redesign the hardware for energy efficiency. Now the challenge, of course, is if we take a look at applications like autonomous navigation, actually use a lot of data. Right? So for example, if we think about semantic understanding, which is basically assigning a label to each of the pixels in the image, so being able to indicate that these pixels belong to the ground and these pixels belong to the sky or a person, this can be very expensive. So first of all, we often want to do this at a high frame rate, especially if the scene is changing very quickly or because we're moving very quickly. We often want to have high resolution, so this enables us to see objects that are far away. And then finally, if we want to support objects, identifying objects, let's say at different scales, you might also have to do data expansion, for example, build an image pyramid, and this will further increase the size of the image by 1 to 2 orders of magnitude. Now, another type of data that we need to process for autonomous navigation is the task of geometric understanding, which basically means to understand where the pixels are in the real world and to construct a 2D or 3D map. And you can imagine the longer that you travel, the larger the map actually grows in terms of size, and that's going to be a lot of data to handle as well. So in general, if you want to have robust, long-term navigation, you're going to have to deal with a lot of data, which of course is a challenge because we just mentioned that data movement is what really dominates energy consumption. So I'll give you some examples in terms of some of the work we've been doing at this space to address this. So the first task that you would do in autonomous navigation is the task of localization. Basically, you want to determine the location of where the robot is and where it's actually facing. And a typical way of doing this is using what we call visual inertial localization, which is basically fusing in image or visual data along with inertial data that you would obtain from an inertial measurement unit. So this is an accelerometer or a gyroscope. And then you would fuse this through a process called visual inertial odometry. And then the outcome of this is basically the 3D position of the robot in the 3D world. So you can see here that we're streaming in a video sequence, and then here in this graph on the upper right-hand side, we're estimating the 3D position of the robot as well as where it's actually looking. If you're navigating in an unknown environment, you also need to generate a map of the environment that you're navigating. So we've been looking at how do you do this in an energy efficient way. And so in collaboration with Sartesh Karaman and the Aeroastro department, we were able to build a custom or specialized hardware called Navion, which is the first chip that performs complete visual inertial odometry on chip, and it consumes under 25 milliwatts. And it does all the processing that is necessary for this localization task. So it takes an input from a front end, in the front end from the camera, it does feature detection, tracking, and outlier estimation. It also takes in information from the IMU, and it does what we call pre-integration of the accelerometer and gyroscope data. So basically it's incrementing or fusing the data so that it is summarized at the key frame rate, which is the rate which we care about in terms of updating the pose. And then the backend optimization fuses these two modalities of data into an estimation of the 3D position. So shown here is the Navion chip. It's 4 millimeters by 5 millimeters. And so you can see relative to this quarter, it's quite small. And you can imagine that you could mount this on these small nanoscale type of drones. On this chip itself, you can see that it contains all the different components that we've just highlighted here. And all in all, it can run at up to 171 frames per second while only consuming 24 milliwatts. So when you compare this to a mobile or desktop CPU, we're talking about 2 to 3 orders of magnitude reduction in terms of energy. Now the question is, how were we able to achieve this energy efficiency? So one of the key things that we looked at, and should be no surprise, is how do we reduce the amount of data that we need to manage in this type of system. So again, the first of all is what we did was we fully integrated all of the processing on chip. So we have no off-chip processing or storage. And this is for the primary reason of that we know that moving data on and off chip, as we discussed before, is extremely expensive. Once we put everything on chip, we also want to reduce the amount of data on chip itself. So in the visual front end, we apply very lightweight, low-cost frame compression to reduce the size of the frame or visual information that we need to store on chip. And on the back end, we exploit sparsity in the graph and linear solver. So we don't want to process, for example, values that are 0. We can also reduce the storage cost because you don't want to store 0 values as well. So all in all, by exploiting both compression and sparsity, we're able to shrink all of the storage down to under a megabyte of data. So everything can be done in around 850 kilobytes on chip. And this can be useful in a wide range. This type of processing can be useful for a wide range of applications or a wide class of robots that we call low energy robots. And these are robots that consume under a watt for actuation to interact with the real world. So you can imagine applications such as lighter than air vehicles that are used for air pollution monitoring, miniature satellites for deep space exploration, or origami and foldable robots that can be used for medical application. So as I mentioned, these low energy robotics consume very little energy for actuation. So as a result, consuming also a lot of very little energy for computation is also very critical. Another thing that we looked at is neural networks, particularly in the AI space these days. We know that neural networks is giving really exciting state-of-the-art accuracy on a wide range of applications, so it's really become kind of the cornerstone of AI. However, one of the main challenges is that the computational cost of these neural networks. They often require several hundreds of millions of operations and weights to compute. And so when we compare it to a type of, let's say, visual data processing that we have on all of our phones, which is video compression, this is 2 to 3 orders of magnitude more complex. So this is a significant challenge because basically we'd like for AI and neural networks to be as ubiquitous as video compression, but it's much more complex. So we have to look at various ways with which we could address this. So the first thing to recognize is actually when we talk about neural networks, it's just a bunch of multiplies and accumulates. So actually high throughput or high parallelism is possible, and so we can achieve high throughput, meaning that we can run very quickly. The main challenge, which should be no surprise, is actually the memory access, which is serving as the bottleneck. To give you guys an idea of why it is, if we take a look at one multiply and accumulate, right, we typically need to have 3 reads. So there's 3 inputs, the filter weight, the image pixel, and the partial sum. And we would generate 1 output or 1 write, which is the partial sum. So that's a 4-to-1 ratio in terms of memory access to compute. And then as we mentioned earlier on, each of the memory access, in the very worst case, let's say if they came from DRAM access, which you would try to never do, would be 2 orders of magnitude more expensive than each operation. Right? So if you think of AlexNet, just as an example, which has 700 million multiplies and accumulates, it would require 3 billion memory or DRAM accesses to do that kind of processing. And so we very much would want to avoid that. And this, of course, also holds for even more modern DNNs as well. However, there are opportunities that we can leverage to address this, particularly that a significant amount of the input can be reused for multiple operations. Right, so for example, if we think about convolutional neural nets, which is widely used for image processing, we often will take a filter and you will convolve it with an image. And so that means the pixels and the weights are going to be used multiple times, just in different combinations for different operations. Right, so the same pixels and weights will have multiple reuse. Similarly, typically what you would do in neural nets is that you apply different filters to the same image or the same feature map to generate multiple output channels. And so what that means is that each pixel in the image is going to be reused multiple times across the different filters. And then finally, if you process more than one image at a given time, which we often refer to as a batch of images, that means that each weight in the filter can be reused multiple times across the different images as well. So there's a lot of input data reuse opportunities. And so then what we want to do is we want to design hardware or memory architecture that can allow us to exploit the data reuse, in particular at the low-cost memory. And so what is a low-cost memory? A low-cost memory is basically a small memory, typically smaller, under a kilobyte, so small memory typically doesn't require much energy, which is located very close to where the compute is happening, because we know data movement is expensive. And so let's say we have an architecture that looks like this. You have these processing elements with the local memory and the compute. You have an array of these processing elements. They talk to a global buffer, and then they cross to a DRAM. You get the following approximate energy breakdown. So if a multiply and accumulate in the ALU is 1x, reading from a register file or a very small memory near that compute, which is under a kilobyte, will also be 1x in terms of energy. If we read from a neighboring processing element, it might be 2x the energy. Reading from this larger memory, this global buffer, which is 100 to 500k bytes, would be 6x the energy. And then going to DRAM, as we mentioned before, is going to be very expensive. So the key message here is that the farther and the larger the memory is, the more power it will consume. Now, so the ideal situation is that we want to read most of our data from this very small register file because it's going to be very efficient, this very small memory. But the challenge is, as we recall, is that we need to process that very large neural network, so that's on the orders of hundreds of millions of weights, for instance. So what we actually need to do is we need to break that larger neural network into a bunch of chunks, and then we then need to figure out what order should we process these chunks in order to reuse as much data as possible from these small memories. And so the order in which we process the data in is basically what we refer to as a data flow. And we've optimized that data flow, and we figured out the best order to reuse the data. And this resulted in a chip that we called Iris. And so Iris basically exploits data reuse within those smaller memories, and as a result, we can reduce the amount of memory access from the buffer SRAM by 100x, and then we can reduce the amount of memory access from that very expensive off-chip DRAM by over 1000x. And here's the small Iris chip. It's a 4mm by 4mm chip and 65 nanometer CMOS. And all in all, it consumes under a third of a watt. And so when we compare it to mobile GPUs, it gives an order of magnitude energy reduction. This is in collaboration with Joel Emmer. This is the first version of Iris. More recently, we had a latest version of Iris that we published this year, and that gives another additional order of magnitude energy reduction on top of this. Finally, I just want to highlight some of the exciting applications that exist in the context of applying energy-efficient AI to healthcare applications. So in collaboration with Thomas Helt, we've been looking at the challenge of monitoring neurodegenerative diseases. So we know that dementia affects 50 million people worldwide today and continues to grow. And one of the challenges in this space is how do you get assessed for having this disease. So often what the patient has to do is that they have to go into the clinic to see a trained specialist, and the trained specialist will ask them a series of questions and that make them do certain tasks like drawing a clock. And the challenge with this is that it's often very expensive and time-consuming to this. So as a result, the measurements are taken very infrequently, so maybe once or twice a year at most. It's also mostly qualitative. So if you go to different specialists, you might get a different assessment. And even with the same specialist, there might be a lot of high retest variability, so the assessment might change under repeated tests. What's been really exciting is over the past few years, it's been shown that there's a correlation between eye movement and neurodegenerative diseases. And so we can use eye movements to quantitatively evaluate the severity or progression or regression of a various neurodegenerative diseases. So for example, you can imagine using eye movement to be able to assess whether or not a certain drug is helping or not with a given disease, and this is used as a complement to the specialist's assessment. Currently, the ways in which this is actually done requires very high cost and specialized cameras, um, and you need to go into the clinic to do the evaluation. And so, in collaboration with Thomas, what we've been looking at is whether or not we can actually perform these assessments using a smartphone and collect these eye movement features. If we're able to do this, would enable low-cost in-home measurements, so this can be done very frequently. You can collect a lot more data to help the specialist in their assessment. And of course, what's really critical here is that we want to be able to do the processing efficiently on the phone itself, because we're dealing with very sensitive data. So in summary, energy-efficient AI extends the reach of AI beyond the cloud by reducing its dependency on a communication infrastructure, enabling privacy and low latency processing. And this allows AI to be used in a wide range of applications, ranging from robotics to healthcare. In order to achieve energy-efficient AI, we need to take a cross-layer approach from designing energy-efficient algorithms to specialized hardware. And we believe this is going to be critical to the progress of AI over the next decade. So if you're interested in finding out more about this research, I invite you to visit the website listed below. You can also follow our Twitter feed for updates, and feel free to reach out to me by email as well. Thank you.